Okay, so then we can start.
Hi, good afternoon, everyone. So, welcome back to ML Lecture Series 3 of the workshop. As you all know, Dr. Shobhanshu Bhattacharya have already taken a very helpful tutorial on foundations of data sciences, and today he will be talking about the deep neural networks. Hands-on session will be followed after the talk. So, hope you all enjoy it. And Dr. Shobhanshu, please take over.
Okay. So good afternoon, everyone. Is my screen visible? Yes. So I think my screen is visible.
Yes.
Okay. So I can switch on also my. Give me 1 minute. Okay. I can just switch on my camera. Okay. So. Okay. So. Yeah. So as many of you might already know, today we are going to discuss kind of two related and especially in today's context, very, very important topic. The first one is neural networks and the second one is optimization. Okay, and the reason they are related is because in order to train neural networks, you need to know a bit of optimization. Okay, so this is not to say that the other machine learning methods don't need optimization. Okay, so the other machine learning methods that I have described in the first lecture about linear models, okay, let's say logistic regression and things like that, those need optimization. And moreover, I think in the second lecture, what Professor Chatterjee would have covered, there also he would have covered a bit of optimization. But the difference is that the tools that you use for you know those particular models, those tools implement the optimization inside. Okay, so for example, scikit-learn will implement many different optimizers, and you simply need to choose the choose an optimizer, or even many a times the default optimizer that is already chosen by the package, which is the scikit-learn package, is good enough. Okay, so that's the idea. But here in neural networks, as we shall see, because the architecture of your neural network can change, okay, so it is not possible for you to use the tool without knowing a little bit of optimization. So first I will I will describe the basics of neural networks, and then I will describe today what is called convolutional neural networks, which is used for image analysis a lot. Okay, and then I will maybe talk about a little bit of optimization method. Okay. 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 So what are neural networks? Okay. Uh, so neural networks are this class of models where we can say that all the processing is done, all the learning, processing, whatever you want to say. Okay, a neural network at some point in time people also talked about it as a computational model, not just a machine learning model, but today we will stick to only machine learning. Okay, so so what they do is so all that happens in what is called a neuron. Okay, so and what we will see is that you create a network of neurons which then help you in doing the entire learning. Okay, so so then actually so the question is, what is a neuron, right? So a neuron in the context of a neural network is a very specific and simple processing unit. So what does this processing unit have? So this has many inputs. Okay, so in this particular example, you can see x1, x2, x3 are inputs. Okay, it has many weights. So for example, w1, w2, and w3 are weights. Okay, it can have a bias value. Okay, which is in this case, let's say b. Okay, and then it has what is called an activation function. So this is given by this particular sigmoid shaped curve that you can see. Okay, and then it produces one single output. So in a neural network, one neuron produces one output. So we will see a generalized version of this, but at the when we talk about pure neuron, so it uses only one output, or it produces only one output. Okay, and what is the computation that the neuron does? So it basically does this summation over I, wi xi plus b. Okay, so if you see, you will immediately remember that this is what the linear model was. So, and you are absolutely correct that the first part of it is exactly as a linear model. So it does an aggregation. So now you can think that a linear model, okay, is like one neuron of a neural network. So that is one way of thinking about it. Okay. Okay, very good. So this so this is a so this is the computation. Additionally, what happens is this aggregation, this whole aggregation, which is the weighted summation of inputs plus the bias. Okay, this is passed through this activation function S. Okay, and then that whatever is the resultant is actually the output of this particular neuron. Okay, so this is what a neuron does. Okay, and so this is basically saying the same thing. Typically, your activation function will be some kind of a nonlinear function. So it does not make a lot of sense to have a linear activation function, simply because what you will do is you will make a network of these neurons, and a network. So the aggregation function is already a linear function. If the activation function is also a linear function, it is just a sequence of application of linear functions, which leads to one single linear function, and that is not desirable for many purposes. We will see very shortly. Okay. So the activation function will be a nonlinear function for sure. Okay. Typically, it will be a squashing function, something like the sigmoid function that we have seen in the context of logistic regression. Okay, or many other activation functions like the ReLU function, which is called the rectified linear unit, and so on and so forth. Okay, so we will maybe look at some of them. Okay. Okay. Yeah, so this is what I was talking about, the activation function. So, instead of, so there is another point of view of this activation function, which is like a motivation from real neurons. So the way, our actual neurons work is that it receives a certain input potential. So it can receive this input potential from a lot of places. Okay, and then when the sum total, or the aggregate input potential crosses a particular threshold, the output of this neuron fires. Okay, and this is kind of captured by this particular mechanism, which is the thresholding mechanism, which says that if your weighted summation of the input to this neuron crosses this threshold, whatever this threshold value is, okay, which is probably going to be the bias value, okay, the output will become from 0 to 1. Okay, so it is not an exact approximation. In fact, it is a very poor approximation of a real neuron. This is well understood. But you know, that is another motivation of this activation function. Okay. Okay. Now the question is that why do we need to go into this neural network? Okay, and this sort of thing was identified very early during the machine learning. So in fact, in 1950s and 60s, there was this person called Rosenblatt. So they had a single layer perceptron. So single layer perceptron is nothing but something like a you can say a linear model, like a linear regression model, or something like a logistic regression model. Okay. Now and then it was fed the features as the input. Okay. So now in this case, so the problem is that of non-linear separability, and that problem is very well embodied into this simple problem called the Zord problem. So what is the Zord problem? The Zord problem is that, you know, suppose your function, suppose your inputs are x1 and x2, and these are binary inputs. Okay. So Zord function, as you know, is a binary function. So input is binary, output is binary. But we are plotting it in a continuous plot here. So x-axis is continuous and y-axis is also continuous. Okay. Just to illustrate the point. Okay. So then your Zord function is actually this C function here. Okay. So as you can see, for the other gates like AND and OR gate, you can classify, you can have a classifier which will learn the difference between 0 and 1. Okay. So in other words, what you're trying to do is you're trying to learn a linear separator which will either produce 0 or 1 based on the input, such that it is able to map these gates. Okay, so it's able to learn this gate. Okay, and it's able to learn AND OR gates, as you can see. So here the function value is 0 if you know, if it is if the circle is white. If the circle is black, then the function value is 1. Okay, so that is the idea. So for AND and OR, it's able to very easily learn the function, and I have shown the linear decision boundary. Okay. Now this, for this Zord problem, you see it is a linearly non-separable problem. Okay, because there is no linear decision boundary that can actually learn this. Okay. So this is a very simple motivation for a situation where you know, we cannot, I mean, so we just cannot learn using the linear functions, this particular function. So if your input function, if you're trying to learn a Zord function, there is no way that you will be able to learn it through the linear function. Okay. Okay. But then the question is, can we learn it through a combination of many? So why are we going here, right? So we know that we are able to learn linear functions very well. Okay, linear functions followed by a non-linear activation. We know how to learn this. So then people ask this question that, can we do this learning with, for example, a combination of many such linear functions? Okay. So how will that work? How will you combine many such linear functions? Okay. So then people come up. So each linear function, we have already called it as, it's not exactly a linear function, but so that's why let's call it a neuron. Okay. So it's a linear function followed by a non-linearity or an activation. For simplicity, always think that the activation is the threshold activation or the sigmoid activation, something like that. Okay. So can we use a network of these neurons, okay, which implement this linear function followed by a non-linearity, to actually learn this kind of function? Okay, so the answer is that yes, it can be done. So what can happen? So for example, so how can we do this? Okay, so for example, we can let's say we can say that so we are able to learn and or using linear functions, right? So what we can say that, let's say we will say that so one very you can just check for yourself, a very simple representation of XOR is actually this x1 and x2 bar, or x1 bar and x2. Okay, so you can check that this is a very simple representation, and that's what we are doing. So this first, so you see the input 1 and 2 are x1 and x2. Okay, now this 3 we are thinking will compute x1 and x2 bar. X2 bar is the negation of x1. Okay, and that's very easily learnable, okay, by a linear separator, as we have seen. Similarly, x1 bar and x2 is also very easily learnable by 4. Okay, and then this 5, which is not taking input as x1 and x2, that will not work, but it takes the output of this 3 and 4 as input and then tries to learn this OR function. Okay, so if it does this, then we are able to create a network of neurons which at least potentially can. So here notice that we are not saying, when we are providing the the network, it's a general network, and we are not setting any weights or anything. So the weights will be learned by the data. Okay, but we want to just ensure that there is at least one combination of weights which can learn this XOR function. Okay, and that we have just explained that it is there, it exists. Okay, and in that case, basically, since there exists a set of weights, hopefully, if you have a good enough learning algorithm, it will be able to find those weights, because that's the job of the learning algorithm, right? Okay, okay. So now let me generalize this here. So what have we done here actually? So we have said that we are going to create this network of neurons. Okay, and uh, and so what is the network here really? Okay, so I am assuming most of you understand all of you understand what is a network. So network has nodes and connections, right? So nodes and connections. So each node of the network is either an input or a neuron, as shown here. Okay, so the round nodes are neurons. Okay, and these box nodes are inputs. Okay, so sometimes are also called units, because these are the things which are doing all the processing. Okay, and then there are these connections. Okay, so different nodes are connected to different other nodes, and there is a particular architecture that we are talking about. Now this architecture is very important. So what are the properties of this architecture? So first of all, what do this connection mean? So this connection means two things here. Okay, the first one is that corresponding to each of these connections, there should be some kind of a learnable weight. Okay, so this is the first thing. Okay, so this is one thing. Okay, fine. So the second important thing about this connection is that actually these connections also give you some kind of a dependency structure. So what do I mean by dependency structure here? You see, now that we are talking about networks, we can talk about very general networks. Okay, so let me just can I use the just for 1 minute, just switch it. just I want to give one example to everybody to illustrate the point. Because remember, what we are going towards is more generality. Okay. So let me draw a network for you. Okay. Okay. So let's say this is input. Okay. And let me draw this network. Okay. And let's say, this is the output. Do you think this is a neural network? So the answer is no. Okay. So this is the input. Okay. So this is not a neural network. Okay. And why is this not a neural network, right? So because there are two things which are important. Okay. So first is that you have to have weights that will learn, but you also have to have a sequence of computational paths so that the outputs of all the neurons can be computed. Okay. And this cannot happen in this particular case simply because, let's say you have the input value. Okay. Now, in order to compute this output, you need the output of this value and this one, right? So these are the two things that are, so this is W1, this is W2. Okay. So actually, so let me call this, let's say input X1, then, okay. And this, so let's just not, yeah, so this is X2, X3 and X4. Okay. So what is the formula for X3 then? Okay. It is this, okay, plus W1 X1 plus now W2 X4. Okay. Now this is the problem because X4 you don't know. Okay. And in order to know X4, you need to know X3. And in order to know X3, you need to know X1. So you see, this particular neural network is not even computable. Okay. So there is another very important connotation of the connections of this particular neural network, which is that the neural network, the connections are weighted, okay, are directed, which means that the connections have a direction. So in this case, the connections have a direction from input to the hidden units, and here there is a direction from the hidden to the output units. Okay, and this is called a directed acyclic graph. Okay, so whenever the connections have a direction, these are called directed graphs. Okay, and these graphs should be acyclic. The directed graph should be acyclic in the sense that there should not be any cycle between, there should not be any directed cycle between the nodes. Okay, so this is the first thing. Okay, now you can easily understand that if this is the case for the network, okay, then you can organize the networks in this manner. Okay, what is this manner? Where you can organize them in layers. So all the input units for which you don't need any computation come in layer 0. Okay, the next layer is those nodes, okay, which take as input the layer 0 nodes. Okay, and then that's it, layer 0, or yeah, so in this case there is nothing else. So layer 0 nodes, and then its output is computable. Okay, so in general you can have any number of layers connected like this. Okay, and typically you will see these hidden and output units said, but in modern neural networks more and more this distinction is not made anymore. Okay, which are the hidden units and which are the input units and which are the output units. Rather, all of them are neurons. Okay, and these neurons are organized in layers. Okay, So layer 0 is typically input, but there can be many output at many different layers. Okay, and there can also be other inputs at some intermediate layers. Okay, but yeah. So but the main thing here is that there is a dependency that layer I, when you are computing the output of a neuron at layer I, your inputs you will need are only till layer I minus 1. So it could be layer 0, layer 1 till layer I minus 1. Okay, so this is the key idea. We'll see, we'll go into in detail. Okay, so this hidden layer, this is kind of an old terminology. So yeah, okay. So now let us go into this thing. Okay, so now then what are these deep neural networks? Okay, so in the way that I just described, okay, the depth of a neural network then becomes very easy. It is the number of layers. Okay, so so the number of layers that you need in order to compute all the outputs or all the neuronal outputs of a particular neural network. Okay, and this is basically I don't know if many of you know this, but these deep neural networks kind of went through a revolution during the 2010. I mean, from 2010 to 2015, you can say something like this. So before this, we used to know about, so as I mentioned, right? So for one hidden layer, which is like depth 2 neural network, we used to know from, let's say, 1960s or 1970s. Okay, by the time we were in 1990s or 2000s, we could train very easily 3-4 depth neural networks. Okay, so and these were also used in many applications. Okay, but then the neural network kind of saturated because we could not effectively train much deeper neural networks. Okay, so what happened during this 2008, 9 and 10 is two technologies got developed. Okay, so what are these two technologies? The first one is what is called a GPU computing, which I will show today. Okay, and the second one is what is called an optimization technique, which is the stochastic gradient descent optimization technique. Okay, these two together made it possible to train very deep neural networks, and I will demonstrate it today. Okay, okay. So this is the main thing. Okay, so
layer. So we are excluding the output and input.
that's this thing. So you typically include the output but exclude the. So if there are 3 layers, you typically exclude the input layer, because input layer there is no computation. So with one hidden layer and one output layer, the neural network will be called a depth 2 neural network. Okay, so typically when we say deep neural networks, we talk about something like, let's say, depth 5 or more. Okay, so that is when because less than, so this is an arbitrary number. If somebody can say that depth 4 neural network is also deep neural network, but yeah, so it's not a threshold or anything, but typically as you go deeper, like if you go to, let's say, depth 10 or something, training of such neural networks becomes very hard. Okay, so now okay, so now that we have already discussed training of neural networks, so at a very high level, how do we train these neural networks? And as you can remember from our previous discussions, it is very similar to how you train the linear models. So what do? You simply say that you have a data set of inputs and the correct outputs for those inputs. Okay, so this is the supervised learning setup. So, and then with this data set, what you do, you give the input for each, you go over the training data points in a loop. Okay, you provide each training data point as input to the neural network, and then you get the output of this neural corresponding to this training data point at the output of the neural network. Okay, then you compare this output to the already correct output data that you have, that is the ground truth label data. Okay, and the way you compare this is using what is called a loss function. So we have already seen one loss function, which is the squared loss. Okay, and there are also other loss functions, like we have seen, for example, the binary cross entropy loss, which is the loss function corresponding to the logistic regression, okay, model. And then there are also other loss functions, which is like, for example, multi-class logistic or multi-class classification. One uses something like a cross entropy loss, not a binary cross entropy loss, but a multi-class cross entropy loss. Okay. Okay. So so once you have compared the output.
There is one question. Where are the connections here to send the errors back, and where to send error to the nodes of the hidden layer?
Sorry.
Where are the connections here to send the errors back? First question, and where to send error to the nodes of hidden layer?
Okay, so I have not. So this is like a little bit forward-looking question. So let me go through with that portion, and then maybe we can answer. Okay, okay. So this is the idea, and then okay. So and then when you propagate, yeah. So when you propagate, so once you compute the loss, okay, what do? You minimize the loss. And how do you minimize the loss? You minimize the loss by adjusting the weights. Okay, so we haven't talked about propagation yet, but we use something called back propagation to adjust the weights. Okay. Okay, so this is the overall algorithm. You give the input, you get the output, compare it with the ground truth output, calculate the loss, minimize this loss by adjusting the weights. Okay, so this is the key idea. Okay, so the main question, I think that is the question that was also asked in the chat, which is that how do I adjust these weights? Okay, and this is another important technology which was developed again in the 1970s, which is the back propagation algorithm. So what does the back propagation algorithm do? Okay, so I have described this method of how you can compute the output label from the input feature vector. So I'm not going to again describe it. So you can see that you can make a prediction, calculate loss, and now the way to basically adjust this weights is using the gradient descent. Okay, so what does this mean? This means, see, now you have to understand this, that the loss is a function of the weights. Okay, so the total loss is a function of the weights. Okay, so here, for example, inputs are x1, x2, x3. Okay, y hats are the calculated outputs, and y's are the true outputs. Okay, so y hat and y, when you compare, you get the actual loss. So the computation happens like this. First you pass in the input, you calculate each layer, you get the output, and then you evaluate this loss j, yi and yi hat. Okay, okay, and then now you have to calculate the gradient of the loss, which is this j, with respect to the parameters. Okay, okay, yeah, okay. So yeah, so now, yeah, you see, f is a complex computation involving many weights. Okay, so how do you compute this? Okay, So the way you compute this is basically, so what do you have to do? You have to compute this quantity del of j, del of wk, okay, for every weight in the network, okay. So for every weight wk, remember the weights here are all these connections, okay. So each connection is a weight. So for each of these weight, okay, you have to compute del j, del wk, okay. So that is the job, okay. Okay, so now sometimes we deal with vectors, okay. So up till now we were talking about, so let us still go with numbers instead of vectors, because that will make the computations easy, okay. So let's say each weight, yeah, so we have each weight and yeah, okay. So each connection has one weight, okay. Now let's say we want to compute, so this is W3, this is W2, this is W1, okay. So we want to compute del j, del W3, and let's say we are using squared loss, okay. So how will we compute? We will compute it as basically del j. So what are the things that we are computing, right? So there is a activation here, okay, which is this sigma, let's say, so we are calling these activations A3, okay. So A3 is basically the activation of the third layer, okay. So then we have this del j by so del j by del loss times del j by del L3. So is this, yeah, so is this clear? Okay, should I describe it? Okay, so if it is not clear, please let me know. So basically what I'm saying is this this node is computing the j, okay, and this node is A3 and this node is y hat, okay. So y hat is a function of W3, okay, and A3, okay. So and j is a function of y hat and y, okay. So del j of del W3 is going to be del j of del y hat and del y hat del A3. Is it clear? Or rather del y hat and del W3, okay. So and that turns out to be this, okay. So the first one is y hat minus y, which is the del of loss del y hat, okay. And the second one is del y hat del A3 del W3, okay. Del A3 del W3, as you can understand, is going to be A3 because it's basically so and here we are assuming that the activation is linear, okay. So yeah, actually in the final layer the activation is linear. Here the final layer the activation is linear, okay. That is why we are getting this, okay. In the previous layers, okay, you will see that it keeps on getting multiplied. So this so you just have to trace the path backward, okay, through this network in order to compute this gradient, okay. And here is the formula I have given for this one. I mean, you have to really get down to the calculus to derive it, but essentially what you do is you calculate the gradient of the activation function and then pass the input to that particular activation function. So Z3 is the input to the activation function, and then you multiply it with A2, okay. So A2 is the, so Z3 is just to be clear, Z3 is the aggregated input, okay, which is the input to the activation function, okay? And A2 is the second layer activation output, okay. So and so on and so forth. So this way you can compute W3 and W1. I am leaving out a lot of details here because that is kind of unwieldy, but essentially this is what backpropagation does, and this you don't have to bother, as I will describe with the tool. Okay. Okay, so this calculation, this is the detailed calculation which I will skip here. We can go into, I mean, you can see it here. Okay, again the same thing happens, that every time you want to propagate something back from the previous layer to the current layer, it turns out to be a multiplication of the previous gradient, okay, times these two quantities, which is the local error signal and the local input signal. So if you go back to here, you see, yeah. So all you have to do is you have to multiply this. So you already had this y minus y hat and then W3. You only have to multiply it with this sigma dashed and A2. Okay. Yeah. So sigma dashed and A2. Okay. And so on and so forth. Okay. Okay. So anyway, so this is, you need not bother about this. So let us go ahead. So now a little bit about the software that I'm going to describe later. So what happened in the, in the last decade is that there were some softwares written which could actually implement this whole computational graph concept very, very efficiently. Okay, and we will see how to use this. So these softwares, they have basically nodes, okay, and directed edges, as I described. So the nodes represent some computation and also the output value of that computation. Okay, so each node again. Okay.
Is feed-forward neural network and backpropagation-based feed-forward network are same?
Okay, so what I described right now is feed-forward neural network, and backpropagation is not a neural network. Backpropagation is an algorithm to update the weights of a neural network. Okay, so backpropagation is not a neural network. Okay, so backpropagation algorithm, like I described right now, computes basically the gradient of the loss. It can compute gradient of anything, but in particular of the loss with respect to the weights. Okay, so that is the essential functionality which all these deep learning softwares provide. Okay, that is the only thing that you need. Okay, and that's what I'm coming to here, that yeah, so basically what you will do, as you shall see, you will basically define these computational nodes. Okay, and now earlier I was saying that these nodes can be aggregation, weighted aggregation, and then followed by any nonlinear function. So that still remains. Okay, but the key idea here is that there you can choose from a whole variety of different types of weighted aggregation. We will see one very specific form of weighted aggregation, which is the convolution. Okay, very different from the feed-forward type weighted aggregation. Okay, and then we can also have many different types of nonlinearities, which we will see. Okay, so here is a neural network, for example, which is implementing this. Okay, so you suppose your y hat is this W transpose X, and S1 of that. So sorry, not S1, but sigmoid of that. Okay, so your y hat is W transpose X and then sigmoid of that. Okay, and then there is a loss that you can compute. So there will be another node here, which is the loss computing node. Okay, which computes this L y hat. So to that node, you will give as input the y and the y hat. Okay, and then you can do so you can do all the computation. Okay, and then you can see that you can propagate the loss back, and the propagation the propagation is somewhat like this, what we have described. Okay, only thing is yeah, so here we are sort of yeah, so we are propagating you know, y minus y hat, which is the gradient of the loss with respect to y hat. Okay, and then y hat s1 remember is the input to the activation function. Okay, and then this del of s1 del of w1, so this sigma hat times x1 are the things that are going back, and this gives you the del of L del of W1. Okay. Okay. So so this is how the computation goes. Okay. And there are many different types of I've just given some examples of some computation graphs. Okay. So this is what the deep learning softwares they allow you to build. Okay. Okay. So what I have described till now is feed-forward neural network. Okay, so all neural networks. In terms of uh, in terms of the terminology, uh, you can say if so. So here you see, actually, let's go back here a little bit. Okay, so this layer is also called fully connected layer. So it's feed-forward neural network. So it has to be a feed-forward neural network. But also this is a fully connected layer. So what does this mean? This means that all the neurons in the next layer are connected to all the neurons in the previous layer. You can see, right? And there are no other connections. So for example, neurons in these layers are not directly connected to neurons in this layer. So this is what is called the feed-forward layer. Okay. For image processing, there is another very crucial type of layer which is used, which is called the convolutional layer. Okay. So before we go into convolutional layer, we have to understand this, that this fully connected neural network is a very generic type of neural network. So which means that so there are two things that happens. Okay, so if you have a fully connected neural network, the first problem that happens is that you have a lot of weights. Okay, so so let's say so let me give you some idea, right? So let's say you have a 254 cross or yeah, so let's say you have a let's say 200, so 200 cross 200 image, let's say. Okay, which means what is the number of inputs now? It is 40,000. Okay, so your number of input nodes is 40,000. Okay, now suppose, so if you have a, let's say, neural network where your input is of size 40,000, you have to have the next layer something like maybe at least 1,000 or something like maybe 5,000 or 10,000, because otherwise you are compressing a 40,000 length thing into a very small thing, right? So that means, so suppose you are having a hidden layer, the first hidden layer of size 10,000. Okay, then what happens is that the number of weights that you have, the number of parameters that you have is 40,000 cross 10,000, and this is something like what, 400 million. Okay, you are already trying to train 400 million different weights. Okay, just one hidden layer. Okay, so this is not doable. Okay, so then what do you do? Okay, so then you say, okay, this is not what I want to do. Their images, they have structures. Okay, so what is the structure? That there is a spatial structure to the images. If you see an image, it's highly likely that one pixel, which is two nearby pixels, will have roughly the same value. Okay, so then what do we do? Okay, So we form these convolutional filters, which will extract features from these images. Okay, so let me give you an example of a convolutional filter. So this will make things very, very useful. So here, let's say this is your input, okay, to the left, okay, and here is a kernel, okay. So this is a kernel. So here in this particular case, the input is also a 3x3 image, and the kernel is also 3x3. This need not be the case, okay, but just for this particular example, this is what has happened, okay. So then what will be the output? The output will simply be your this, okay. So your output will be, you multiply the corresponding pixels with the corresponding kernel values. So 3 gets multiplied with -1, 2 get multiplied with 0, and so on and so forth. And then you add, and whatever is the output is put in the center of the output image. So for a convolutional neural network, the input is an image. So now compare this to what we had already seen, right? So in case of fully connected layer, okay, we had an input, we had some weights, and we had some output. Here also same thing. We have an input, we have some weights. So the weights are in the form of a kernel, and we have some output. But instead of everything getting multiplied with everything, what we have here is we have this special form of aggregation now. So it's not like everything gets multiplied with everything and then gets summed over. We have this, the aggregation operation is now a convolution operation. So this operation that I just described here is called the convolution operation. Okay. So the aggregation operation is a convolution operation where the corresponding guys get multiplied. Okay. So this is the first part. Second thing is that you now move it over. Okay. So I don't know if I have. Yeah. So this example will show you even better. Okay. So consider this red channel here. Okay. This is the input image, and the pink image here is the kernel. Okay. So the red channel is showing the input image, and it is of size, if you see, it is of size 5x5. Okay. And you are putting this pink kernel, okay, on it, which is of size 3x3. Okay. Right now we are going through the black kernel, but anyway, so we have all these kernels. Okay. So these kernels are getting multiplied and then added over, and then the corresponding value is getting populated here, as you can see. Okay. So if your input size is, let's say, 5x5, you see, if you are using a 3x3 kernel, then the output size becomes 3x3. So how do you do this computation? The computation is basically that your kernel size, so your input size minus the kernel size plus 1, right? You can see that the output size is going to be input size minus the kernel size plus 1. Okay. Okay. So this is very nice. Okay. So this is clear. Okay. So now let's go back to this thing. Okay. So why is this useful in case of image processing? Okay. So actually, these convolutions were used even before the discovery of this deep learning. The image processing people were using convolutions in order to do all kinds of image processing operations. So here are some of the operations. Okay. So if you use, so these are hand designed kernels. These are not learned kernels. Okay. So somebody, some expert in image processing has actually designed this kernel matrix. And what is the kernel matrix? It is 1, 1, 1, 1. So all of them are 1. Okay. Now, if you just do a convolution of this particular kernel on any image, you will see that you will get a little bit of a blurred version of the image. Okay. This is another, this is also doing the same thing, but this is a Gaussian blur. Okay. So Gaussian blur is much better. Okay. So This blur will create a very, very blurry image. This Gaussian blur will create a very, very realistically looking image. Okay. Consider the opposite here. Now here the center is high weightage and the pixels around it have negative weightage. So you actually subtract the pixel values which are around it. Okay. So this is actually an image sharpener, and here you can see the original image and blurred image, and here you can see original image and sharpened image, how the difference is. Okay. So this just to give you a feel that how these kernels work. Okay. So these kernels have been studied for many, many years, about I would say more than 20 years. Image processing and computer vision people have been designing and studying these kernels, okay, which through which you can convolve the image to actually get some useful output. Okay. Okay. So here are some more examples. Okay. So this is a vertical line detector kernel. Okay. This is a horizontal line detector kernel. Okay. This is a corner detector kernel, and so on and so forth. Okay. So all these are very, very important kernels. Okay. Okay. So now, how does the convolutional neural network work? So the way the convolutional neural networks work is that so you provide many of these convolutions. Okay, these convolutions operate over the entire image. So typically you will have like a few, like 3x3, 4x4, 5x5 kernels. Okay, typically you will have an odd numbered kernel. Okay, because you need to have a center pixel. Okay, so you have an odd numbered size kernel, but you have many of them. So you can have, in this case we are showing, in this image we are showing 4 different kernels, this green, pink, yellow and black. Okay, but there can be many different kernels. So you will see the networks that we described, they will have maybe 64 different kernels. Okay, so what is this doing? These kernels are actually detecting different features in image. So maybe you go back to now what I was saying. Maybe one of the kernels is doing a bit of a sharpening. Okay, maybe one of the other kernels is detecting horizontal line. Maybe another kernel is detecting vertical line, and so on and so forth. So all these kernels are providing different features from the image. Okay. Yes, I'll come to channel. Yes. Yes, you have.
Just giving one out.
Hmm.
Is it just the sum of two channels, or
It is a weighted sum.
and how do we define this weighted?
The kernel weights.
But for three different layers, we have, if we confound this with the kernel, we have for each equation.
Okay, so yeah, okay, good question. So the question is, what is the computation in 3 dimensions? So I have already shown the computation in 2 dimensions. 3 dimension, it is nothing. So in this case, how many weights? So you remember, in 2 dimension, a 3x3 kernel will have how many weights? It will have 9 weights. So in a 3 dimension, or not 3 dimension, basically, it's like you have a 3D convolution. Okay, in 3D convolution, you have a 3x3 kernel, and in this case, it so happens that your number of input channels is also 3. That is not usually the case. Usually, the number of input channels will be somewhat different. So let's say number of input channels is, let's say 10. Okay, so you will have 9 into, so 3 into 3 into 10 weights. So that is the kernel. Okay, so the size of the kernel is going to be the receptive field size, which is 3. I'll come to it in a minute. Okay. It is a 3D kernel. Okay. So you understand. So in this particular case, for example, the number of weights will be 9 into 3. So 3 into 3 into 3, because there are 3 cross 3 weights for each channel, and there are 3 channels. Okay. So for each output channel, there will be 3 into 3 into 3, 27 weights in this particular case. Clear? So the number of output channels in this particular case is 4. So there will be 4 into 27 weights for this entire convolutional layer. Okay? Everything, yeah, we'll come to that. Yes. So yes, so the weights, whenever I say weights, they are always learnable. Otherwise, there is no point. Because if you are so earlier, people were doing hand tuning of weights, but now any weight is learnable. Okay. Okay. So this is the key idea. Okay. Now you see, yeah. So yeah. So you can see the different types of kernels, but I don't think so. So mostly people use square kernel of odd size. Okay, that is almost always that is used. Okay. Now there is another very interesting concept, which is the concept of padding. Okay. So what is this padding concept? You see what I said earlier, that suppose you have let's say n cross n image. Okay. And you have a k cross k kernel. Okay. Think in 2D. Okay. If you have an n cross n image and a k cross k kernel, what did I say? I said your output image size will be n minus k plus 1 cross n minus k plus 1, right? This is what I said. Okay. Now this is a problem. Why is this a problem? Because you know, you want to finally stack up. So we are going towards deep neural networks. Okay. So, and I shall show you that the depth is actually crucial. Okay. So the depth is what gives you the learnability. Okay. So we are going towards deep neural networks, and your image size is continuously decreasing. Okay. So this is not a good idea. So what is the solution? Simple solution. You do a padding of the image size virtually, not just at the time of fitting, with zeros. Okay. So this is called a zero padding, and typically what will be the padding width? The padding width will be the kernel size minus 1 by 2. Okay. So if it is a 3 cross 3 kernel, you will just pad it with 1 sort of layer of zeros all around the images. Then your size will not decrease, so image size remains the same. So this is one thing. Okay.
One question. Don't we convert an image into gray before analysis? And will we use multiple kernels on the same single gray image?
Good point. Yes. So the answer to the first question, should we convert the image to grayscale? Depends on your application. Okay. If you want, go ahead and convert. If you don't want, don't convert. Number one. Okay. The second question was that should we use multiple kernels for
On the
same
same single
grayscale?
gray
Yes.
image.
Answer is yes. Okay. Because each kernel is a feature detector. Remember always this, that each kernel is a feature detector. And you don't want to detect one single feature. You want to detect a bunch of features from the image. And then based on those features, you want to do the final processing. Okay. So yes, you definitely need multiple kernels.
And he's also asking, what is input channel? Is the channel and kernel same thing?
No, kernel is learnable weights. Channel is the so channel is basically, you can say it's a stack of two-dimensional outputs is called channels. Okay, so if there are many different two-dimensional outputs, so you can also say another way of looking at it is that sometimes we look at it as a tensor. Okay, so each image as a tensor. So the third dimension of the tensor is the channels. That is another way of looking at it. Okay. Okay. So okay. So now okay. So I think this padding is clear. Okay. Yeah. So sometimes we also want to reduce the image size, okay? Because maybe we don't want to always look at. So I was like I was saying that after I have extracted some features from the image at 200 cross 200 resolutions, maybe I have found some features, okay? Now I only want to look at 100 cross 100 image. Oh, sorry, I have to connect. For some reason, it is not connected. Ah, okay. Yes, yes. Okay, thanks. Yeah. Okay, yeah. So, okay. So, okay. So, yeah. So now, yeah. So we can use what is called a pooling layer. Don't bother too much about the nitty-gritty details. We can use something called a pooling layer to reduce the size of the image. Okay. I think let me go a little faster now. So the workhorse of the convolutional neural network is the convolutional layer. Okay. Other layers are, so they are there. I mean, they are useful, obviously, but the main advantage or the main power of convolutional neural networks comes from the convolutional layer, okay, which we have discussed. Okay, so here is an example of a convolutional neural network. You have a convolutional layer, then a ReLU layer. So ReLU is like a rectified linear unit. So if the input is positive, then the input is copied to the output. Otherwise, if the input is negative, then it's 0. Okay, so so this is very commonly used in computer vision. This ReLU activation. Okay. Then there are these pooling layers, okay, and typically, not always, as we shall see, typically what happens is in the final layers, after you have reduced the dimension of the input, you use a fully connected layer, which is this FC layer, to get the classification. Okay, so this is kind of showing that when you pass a car, you get these different feature maps as output, as an output of different layers, and then you keep on doing this to actually then see that it's kind of the final output is having these particular certain neurons firing for the car. Certain other neurons will be firing for the truck, and so on and so forth. Okay. So this is the simple thing. Okay. Okay. Again, I'm going to sort of skip this. I think we have discussed this computation already. Yeah.
So what do we achieve by using convolution and ReLU alternatively? What do we achieve by using conv and ReLU alternatively?
Okay. So as you can understand, right? So convolutional layer is a linear layer. Okay. It's a linear computation. It's a linear, it's a convolutional computation. So if you can also do, I mean, we will see that there are some situations, in fact, some very well-known networks, they also use convolutional layers one after the other. But typically, I mean, so this is an example network. So typically, after a linear layer, you want to pass it through a nonlinearity in order to detect the features. Remember, what is the thing from now feed forward? See, even this particular convolutional neural network is also a feed forward neural network. It's just not a fully connected neural network, okay, but it's a feed forward neural network. Okay, so now you see so whenever you are any feed forward neural network, whenever you are doing some kind of an aggregation, it makes sense to pass it through a nonlinearity so as to detect features. Clear? So that is the purpose of the, so think about the the logistic regression problem, for example. So after you have done all this aggregation, what do? you either say that the output is 0 or the output is 1. Okay, and you pass it through the sigmoid to check this. Okay, so it is detecting this 0 or 1. Now think about it like this, that you are repeating this many so you are trying to, in the second layer, you are trying to compose the output of many logistic regression classifiers into another classifier. So that is the purpose of alternate convolution ReLU. Okay. Okay. So yeah, so basically after linear layer, you have to just remember that after linear layer, it makes sense to pass it through a non-linearity just to detect the features. Okay. Yeah, so these are the, this is the ReLU function. I have described it already. Yeah, I think we can script this. Yeah, so I think one thing I have not described is what is called a stride. So there is another thing that you can do, okay, which is that instead of moving 1 pixel at a time, like I described, you can also move the convolutional filter in order. This is sort of, you can also say that this is, there are many reasons for doing this. One of them is that you just save the computational cost, okay, is that you can move it many pixels at a time. Okay, so maybe 2 or 3 pixels at a time. Okay, and that is called the stride. Okay, so the software or the, typically when people design this convolutional neural network, they also put in a stride value. Okay, and with stride, then it becomes like n minus, so the number of input minus f by stride plus 1. Okay, so you have to divide it by the stride in order to compute the output size. Okay, this output size computation you have to like keep it. Okay, so because whenever you are designing the filter size, okay, for each of this thing, you have to make sure that your filter size and the output size match together. Okay, otherwise it will just give errors. Okay, anyway, okay, so this is about it. Pooling layer we have seen. Okay, so that kind of covers the convolutional neural networks part. Okay, so what are the types of problems that we have been able to solve using convolutional neural networks? Okay, so the types of problems that we have been able to solve include, for example, so the first thing is image classification. So I may be giving you an image which I will describe you during the demo today. Okay, that I may be giving you an image, and that image has only one object. So in this case, let's say the image has a bed. Okay, and you have to classify this image as a bed. Okay, so this is the first. So this is called the image classification problem. Okay, I'll talk about it more. Then they, in the same kind of you can say same kind of data, you have the localization problem. So what is the localization problem? Localization problem is not only do you have to classify the image, the object in the image, okay, but you also have to put a bounding box around it. So you have to say that where this particular object is. So for example, here you can see a red bounding box. So it is not only saying that this is a bed, it is also localizing the bed to this part of the image. So this is another application. Okay. Then there is detection, object detection. Okay, so object detection basically is the problem where your image no longer has one object, but it may have any number of objects. Okay, and what you have to do here is you have to predict all the bounding boxes around all the images, and then you have to also put a label. Okay, so each of the bounding boxes should be accompanied with a label, and the label will actually detect the class of that particular object or the type of that object. So this is the object detection problem. Okay. Okay. Yeah. So this makes it very clear. So single object, you have the image classification problem and image classification plus localization problem, and then you have this object detection problem. And there is another class of problems which you try to solve using convolutional neural networks, which are the segmentation types problem. So here, what we are describing is a problem called the instance segmentation problem. So here, you no longer have to put a bounding box around the object, but you have to actually segment out the object. So what does this mean? This means that you have to identify all the pixels that belong to this particular object. Okay. So this is the problem. This is the problem of instance segmentation. There is another kind of segmentation problem where you say that so in this particular case, other than the object, you are not interested in anything else. Okay, so the objects are, in this case, let's say cat, dog, and duck. Okay, these are the only types of objects you are interested in. Okay, so you are only interested in detecting the pixels which belong to dogs, which is the blue pixels here, which belongs to duck, which is the green pixels here, and which belongs to cat, which are the red pixels here. And in a particular image, there may not be any pixels belonging to cat, for example. So depending on the particular image. Okay, but other pixels are just unmarked. Okay, but there is also this problem called the semantic segmentation problem, where you basically have to classify every pixel of the image into one type. And typically there, what happens is one of the types is the background type. Okay, so basically, if it is not belonging to a particular class, then you say that this is a background pixel. So for example, in this case, whatever is not belonging to cat, dog, or duck will belong to the background. But as you can see, in this particular image, the background is not homogeneous, because some part of the background is green grass, some part of the background is something else, right? So that so the semantic segmentation problem makes more sense when you have like most of the background, some sort of a homogeneous background. Okay. Yeah. Okay. So these are some of the problems that that we discuss. Okay. Okay. So now let me talk about a little bit of how all these. So what I described earlier, during this 2010 to 2015, let's say, there was a kind of a revolution in this computer vision brought about by this deep neural networks. Okay, and I told you that I told you about two different two different factors which led to this revolution. One was the GPU computing, okay, and the second was this frameworks for deep learning, right? So these frameworks for deep learning, they implemented this stochastic gradient descent type algorithms, okay, and they also made it very easy to implement the back propagation algorithm. Okay, but there was another very important component, especially for the computer vision, and that component was this ImageNet challenge. So what this ImageNet challenge did, so this was a massive effort, primarily led by Professor Fei-Fei Li from Stanford University. So what they did, they produced a very massive data set of labeled images. Okay, so what do you mean by so there are, we already had many images, At that time already, there was this, people were already uploading images to the internet. Most of the companies, internet companies like, Google and all other companies, they had large databases of images and users uploaded images. Okay. So what this particular initiative, this ImageNet initiative did is it, you can see it annotated. So the training data set itself had about 1.2 million annotated images, plus another 150,000 annotated images were created for validation and test images. So this is a massive amount of annotated data which was created. Okay, and this sort of provided the data. So you can understand that we are trying to now fit very, very large convolutional neural networks, which has very, very large number of parameters. Okay, so in order to learn all these parameters, we need a very large amount of data, and this initiative this is one of the initiatives that provided that kind of data. Okay. Okay, so now one of the first breakthrough neural networks or convolutional neural networks, which which made people really interested in convolutional neural networks for all the computer vision types tasks is what is called this AlexNet. Okay, this is in 2012 by Krzyzewski et al. And this kind of it won. So another thing that this ImageNet started is, not only did they have, so they also started a challenge. Okay, so they said, what is the best accuracy? So you design your methods, computer vision methods. Okay, and you have to achieve the best accuracy on our test data set. Okay, so that was the challenge. Okay, it was an open challenge. Anybody could participate. Okay, and here what I'm showing is, so see this ILS BRC 10 is basically 2010 challenge winner accuracy. Okay, so that was around 30%. Okay, or rather this is the error. Okay, and this is, I believe, the top 5 error. Okay, not important. Okay, just say that it was some performance measure which was lower the better. Okay, and this was kind of an error rate. So 0% error is the best. Okay, but we will settle for, so here another thing was that the humans had an error rate of around 5%. Okay, so any machine learning algorithm which can do better than 5% error rate is actually doing this task better than humans. Okay, so this is the idea. Okay, now so here it was around 30% error rate. In 2011 it became around 25%. Okay, 2012 AlexNet made it jump to 16%. So this was a huge decrease. Okay, so just to give you sort of a idea that normally if you are able to improve the error rate by 1%, it is a very good paper in a top tier conference or journal in computer vision. Okay, so this is a huge task, or this is a huge achievement, I would say. Okay, and this is also the first neural network based method which actually won this ImageNet challenge. Okay, okay, so now this is the structure of the ImageNet. Now this is not actually this, so this structure is looking more complicated than what it should. The image is taken from their paper, and the reason it is looking this complicated is because at that time the GPUs were not this powerful as we have today. Okay, so what they did, they actually had to use 2 GPUs to train the whole thing. So they split, so they had to do much more work than we have to do today to implement this, which is that they had to split the whole network on 2 GPUs, and these were like very so I think this was in Google. So Google obviously has even at that time had some of the best hardware. Okay, and so but just that the state of development of hardware was not so good compared to what it is today. So this looks very complicated, but it is essentially this. So I have just written down the architecture in the bottom. So it's just one convolution layer followed by one max full layer and then one normalization layer, which was kind of there, but it's not needed. Okay, and then again another convolution layer like this, and then another 3 convolutional layers followed by another max full layer. Okay, and then 3 fully connected layers. So it's just that. Okay, so yeah. Okay, so total depth is what, like something like less than I mean, if you discount this normalization layer, it is I think less than 8, maybe something like 4 or 5. Okay, okay, yeah. Again, yeah. So and this slide kind of enumerates the output shape of the tensor that each of the layers output. Okay, and remember this. So one thing to remember here is that we are now calling even the non-learnable things. So for example, this max full or normalization layers are not really learnable layers. Okay, but we are still calling them layers. So we are using the term layers now a little bit more loosely, which is what is also done by these image processing softwares. Okay. Okay. So so this is the thing, and so we come to the next set of improvements, which is the Vgg network. Okay, and if you go back to this was a huge improvement again, from 16% error to just 7.3% error. And in the same year, actually, this Google Net and Vgg Net, both of them were developed in 2014. So Google Net came first and Vgg Net came second. Okay, and both of them were sort of again another huge jump. And what was the jump? The jump was this. Okay, the jump was they both realized, or they both made the community realize that you can go much deeper, and the deeper you go, okay, the more advantage you have in terms of feature construction and accuracy. Okay, so already at that time this 8-layer network is already very deep. Okay, today we don't call it so deep, 8 layers. Okay, because today I will show you that we can train I mean we sometimes use 150-layer deep networks. Okay, but at that time people were anything deeper than 3-4 layers is very deep. Okay, people were thinking that we cannot learn the weights of these layers. Okay, now this VGG 16 and VGG 19 are 16-layer and 19-layer deep networks. Okay, and very good accuracy. Okay, another thing they added is they said smaller filters are good enough. Okay, and this is kind of detail which I will not cover due to the lack of time, but you can there is some logic by which you can say that you can use smaller filters to actually emulate a larger filter, and then that is actually computationally also more efficient. Okay, and this was also so this idea of smaller filters, combinations of smaller filters rather emulating larger filters, was also used by Google Net. Okay, which actually use just 1x1 convolutions to actually make things more computationally efficient. But Google Net did one more thing. So it I would say brought in this concept of unit. Okay, computational unit. Okay, which is like so they called this Inception Module, and then they started stacking these Inception modules one on top of the other. Okay, and then what they did, so they did 2-3 things. One is that this Inception Module was computationally very efficient. Okay. Secondly, they almost got rid of the fully connected layer. I remember we discussed that fully connected layer are more memory heavy. Okay, convolutional layers are memory and are memory efficient. Okay, so they made this Google Net both computationally efficient and memory efficient, and they use this intermediate training. Okay, so you can see some outputs here from intermediate layers. Okay, and using that they could train a 22-layer deep network. Okay, so this was like much deeper than even VGG at that time. Okay, and again this achieved very good accuracy. Okay, and then there was, and I'm not getting into the details, there was this final a kind of innovation that happened in the convolutional neural network space, which is this which is the development of these residual connections. Okay, and this residual connections, what it did is it allows you to train something like a 150-layer deep network, simply because what happens is it short circuits some of the connections. Okay, so it allows for every layer another path which is the short circuit path. Okay, and this helps in training much deeper network, because you can see that the gradient can always pass through some of the short circuit parts backward. Okay, okay, so with this exposition and I think you remember that yeah, so this ResNet is the one that also, so this was by some of the Microsoft folks, and this also beat the Google Net in 2015, and also the sort of bested the human performance. And after this there was a lot of things, but essentially all the important ideas were already covered. Okay, so let us focus a little bit on the computational efficiency also. You see here this x-axis is how computational efficient, so as we go towards the higher value it is taking more time, and y-axis is the accuracy. So anything that is in the top left is very good, anything which is in the bottom right is very bad. Okay, and so you see VGG 19 and VGG 16 are good, but they are also very computationally expensive, and you can see how many giga operations are needed for computing the output of one particular image. Okay, whereas this Inception you can see is very efficient, and ResNet is kind of here, which is this this network, which is a very good compromise between the two. Okay, especially this this ResNet 18. Okay, okay, okay. So we are done with the convolutional neural network part here. Okay, now what I will do is I will very briefly cover the optimization innovation that was done, which actually allowed this this particular deep learning revolution. Okay, and that innovation was what is called this idea of stochastic optimization. Okay, so it's a very simple idea. So there is a lot of mathematics behind it. I will not go into it. Okay, but is there a question?
Typical set of layers in CNN and where to include max pool and others layers you discuss.
Okay. So that is why I described this, right? So here is one architecture. So is the architecture clear? So you have one convolution, one max full, another convolution, another max full, and then 3 convolution, then one max full. Where is it? Yeah. So then 3 convolutional layers, one max full layer, and then 3 fully connected. So this is AlexNet. Does that answer the question? Okay. So basically, see, there is so like I said, convolutional layers extract features, max full layers reduce the size of the output. Okay. So it is up to the designer of the network how to combine. This is one example which worked very well. Okay. And then after that, the other examples become more and more complicated, and they are not so easy to describe. I have just described the Vgg network. Again, you can see the orange layers are convolutional layers and the blue layers are max full layers. Now, if you ask me why after 3 and why not after 4, I don't know. Okay. So that is not so easy to design. You have to really work with it and work with the application. But I'm giving you some of the networks here which are kind of landmark networks and which are known to work very, very well, and which are used very, very frequently in many commercial applications also now. Okay. So okay. So with that, let me come to the optimization part. Okay. So okay. So now this is an innovation in the optimization algorithm, and the innovation is something like this. You see, we saw that we are now training. So all these networks, right? AlexNet, GoogleNet, and ResNet, these were trained on 1.2 million images. Okay. So now imagine if one image is taking, let's say, just 1 second. Okay. So you remember recall how the training algorithm is working. There is one forward pass and then there is one backward pass, right? And let's say it is taking 1 second, or not even 1 second. Let's say it's taking only something like, let's say, 10 millisecond. 10 millisecond for one forward pass and one backward pass. Okay. Now imagine how much time it will take to do one gradient descent update. Okay. Gradient descent update, remember, is that that you have to optimize the parameters. Okay. So that means you have to do 1.2 million forward passes and 1.2 million backward passes. That means it's basically something like you will take, like 12 lakh 12 lakh seconds, right? Sorry, not 12 lakh seconds, but yeah, I think yeah, 12,000 seconds. Okay. That is actually not much. So 12,000 seconds basically means one update you will be able to do in about 2 hours. Okay. And if, for those of you who have run some sort of a gradient descent optimizer, you will know that it takes typically for anything, like even a small thing, like let's say if you want to learn 100 parameters, it takes at least 100 iterations. Okay. So that means 200 hours. Okay. And you are learning here the number of parameters. I did not say here. You can see some of the estimates here. So for example, for this, it is like not this. So yeah, so you can see that some of these networks have parameters of the order of million. Okay. So then if you do one update, so what is the problem? The problem is that you are going through the entire training data set and calculating one loss function, and then you are doing also the backward propagation and calculating the gradient. Okay. And then you are doing the update. Okay. So that is the problem. Okay. And why we are doing this? Because we only know that we want to minimize the loss function. So this is something we know. Okay. So we have to, and the algorithm that we know is gradient descent, and we have to use that algorithm. Okay. So this is where people started looking into optimization theory and said that no. If you want to optimize a particular objective function, a loss function, what you can do is you can take also stochastic gradients. Okay. So what is stochastic gradient? Stochastic gradient is that you take samples whose average or whose expectation is the gradient. Okay. So if you take such stochastic gradient and you do the gradient descent like updates, okay, not exactly gradient descent updates, but gradient descent like updates, it will still converge to the minimum. Okay. And here, because of the stochasticity, the theory says that it will converge to the minimum in expectation. That is, if you run many such stochastic gradient descent algorithms, then the expected outcome of that will converge to the minimum. Okay. And I will not go into the theory, but essentially what has happened is now, yeah. So you see here, okay. Okay, so let me not go into detail of it. Okay. Basically what happens is your loss is a sum over the loss of different examples. Okay. The total loss that you want to minimize is a sum over the losses of different examples. Okay. And if you take the average of these different losses, okay, and remember these examples are IID, okay, so they are identically distributed. This is a very important thing. Some of the SGD convergence issues happen because of the non-IID nature of the data, but that is a different story. But these examples, at least in a standard machine learning setting, okay, each of the training examples are independently sampled from the underlying problem, and they are also identically distributed. Okay. If this assumption is made, then what you can say that if you compute the loss on just one training example, okay, that is a stochastic estimate of the loss of the entire training data set. Okay. So that is the key idea. That means now you no longer have to forward propagate 1.2 billion training examples. You just forward propagate one training example, back propagate it, do the update, move on. The update becomes 1.2 billion times faster. Okay. So that is the key. That is the one key idea from optimization, which made all this possible. Okay. And this is called the stochastic gradient descent algorithm. Now, what I'm showing here on the screen is how the objective function value or the loss function value looks when you do SGD update. Okay. And this is very different from how it looks when you do gradient descent updates. Okay. In gradient descent update, as you know, if from optimization theory, that it is a descent method. That is, every time you update the parameter, your objective function value either decreases or remains the same. Okay. It never goes up. Okay. But that is not the case in stochastic gradient descent, and which is why the convergence is in expectation. Okay. And which is why there are some practical things you have to do when you try to use this stochastic gradient descent to train your neural network. Okay. Arguably, one of the main things that you have to do is to keep a running minimum. Okay. There are many ways you can do it, but one of the ways you can do is you can keep a running minimum. So whatever is the best parameter in terms of objective function value till the current iteration, you keep that as the current based model once you are running SGD. Okay, so that is a practical trick that you can do to sort of, because otherwise, suppose you stopped at this particular iteration and suddenly just in the last update you made a very bad update, you will land up with a very bad model. Okay. Okay. So so this is all about gradient descent. I will just skip all these things and yeah. So actually, I can talk about accelerated gradient descent a little bit. So one of the things with so in accelerated gradient descent, there are two main ideas that people use. Actually, I have been talking for a long time. So are there any questions or comments, or I mean, just I want some show of hand. How many people really want to know about accelerated gradient? Because while when you try to use these deep learning softwares, you will be given option. So the optimizer is already implemented. So if you know the theory of accelerated gradient descent, you may be able to choose in a more informed manner which optimizer to use, but you never have to actually implement an optimizer. Okay, because most of the optimizers are already implemented. Okay, so just a very high level update I can give. So there are two main ideas that are at play here. First one is momentum, which says basically that if I was moving in a certain gradient direction earlier, I keep a little bit of that direction. Okay. And the second one is what is called adaptive gradient, which is that if I have a certain gradient, so which is basically something like a Newton's update, which is the Newton's update cannot be calculated because so I'm not going into Nesterov accelerated. Nesterov is just a more sane version of momentum, you can say. Okay. And second one is this adaptive gradient, which is basically saying that if you have yeah, so you basically have if in a certain gradient direction the variance is more, and the estimate of variance usually in this particular case is the square of that particular gradient component. I mean, and this comes from like rank 1 estimation of the Hessian, which we are not getting into, but essentially so what you do is you divide the gradient by some measure of how much confidence you have in that gradient. Okay, so combination of these ideas lead to one of the maybe widely used, I can say, optimizers other than stochastic gradient descent optimizer, which is the ADAM optimizer. Okay, which is basically adaptive gradient with momentum. Okay, and this is the optimizer. Yeah, so I think I will stop here. So use ADAM or ADA delta. So ADA delta is also very similar to ADAM, except that it loses out on some amount of initial speed up, which ADAM does. Okay. Yeah, so you use ADA delta or ADAM if you are very confident that your algorithm is going to converge, okay, and it's going to converge fast. Otherwise, you use SGD, stochastic gradient descent, which is more responsive. So in SGD, you have to, one of the parameters that you have to select is the step length parameter. And yeah, so you can select the step length parameter to sort of adjust and make the optimizer converge. Okay, so with this I will stop, and here is kind of a cool graphics which compares how the different gradients, SGD is stochastic gradient descent, that is the red one. You can see that it is going very, very slowly. Okay, momentum is slightly faster, but it has momentum, so it goes away a lot. Okay, so it is not going towards. Yeah, so your optimum is this star point. Okay, so the star point is the one that is optimum. Nesterov is a better version of momentum, so it is the pink one. You can see that it is returning earlier. Okay, and then Adagrad and Adagrad you almost never use because it is not good. Okay, so it has some problems, but it was the first to use adaptive gradient. And then Ada delta and RMS prop and Adam is not shown here, but they are very similar in performance. In fact, Ada delta and Adam I would say are very similar in performance. Okay. Um, okay, so with this I will stop. Yeah, and these are the references. So yeah, I will take any questions if there are any questions. Hmm.
But the increment in the gradient at that location, that increment is not constant for each state.
Okay, so let me go into the SGD update once. Okay, so normally if you see some of the packages, even though they call it SGD, they actually implement SGD with momentum. Okay, and usually they implement SGD with Nesterov momentum. Okay, so this eta is the step length. Okay, in case of pure SGD. Okay, so you basically move eta times the gradient in the direction. Okay, now typically, so what you do is over the iterations you squash the eta. Okay, this is also required for the stochastic gradient descent algorithm to converge. So this squashing, there are different squashing rules. Okay, there are step decay rules. Okay, and there are other sort of so if t is the iteration count, one of the ways to squash it is just multiply just eta by, so your actual learning rate is eta by square root of t. Okay, or sometimes people also use eta by t. Okay, so many of these are there. So I think I have a plot here. So you can see that eta by t will converge faster, but then it may suffer from early convergence and so on and so forth. I would say eta by square root of t or step decay, one of these does best. Yeah, so here I have time based is basically, yeah, step decay is one of the best. And yeah, so what eta by t will converge much faster, but it will suffer from early convergence. Okay, so remember, if eta by t is actually decreasing much faster than eta by root t, your step length is, so if you keep it eta, then your step length is constant throughout the optimization. Okay, so that may suffer from non-convergence. In fact, there is no proof for constant eta that your SGD will even converge. Now eta by root t and eta by t converges for sure. Okay, but yeah, so which one is best? You have to play around with it to understand. But between the two, eta by t converges faster, but it may not converge to the best value. See, there are two things. One is it converges. Second is it converges to the optimum value.
There are two more questions. What if VGG is tried on a strange image, and what is the structure-wise requirement of the dataset to use trained VGG in my application?
Yes. So actually, in the hands-on session, maybe I will try to do some VGG. I will show some VGG. But yeah, so the answer is most probably pre-trained VGG will not work in your application. Okay, but then pre-trained VGG gives a very good starting point to do a little bit of fine tuning. So just 2-3 iterations of fine tuning, and then it can work very well for your application. Okay. And about the pre-processing, basically it does not. So your VGG, I think you have to resize the image to the. So I will show that in the hands-on session. I think it's better to do that. Yeah, I need a break. Yeah. So.
So we shall now take a 10-minute break and then we will continue
We will
with
come back.
hands-on session. Yeah.
Yeah. Okay. Thanks. Okay. Okay. So, hello everyone. Welcome back to the hands-on session. So, what I'm going to discuss today is basically this. Hide the bar. Yeah. Okay. So, what I'm going to discuss today is a very short. It will be a very short demo, and then after that, I will share this IPython notebook uh, with the organizers, and they can share it with all the participants. Okay, and so I'm going to use this framework called Torch. Okay, so or rather, I mean, the name of the package is PyTorch. Okay, and yeah, so PyTorch is the more common version of Torch. Earlier, there used to be a another Torch module based on another which you could use in a different language, but this Python version is very good. Okay. Excuse me. Okay. Yeah. Restart and clear output is what I should do. Is it better now? Huh? Yeah, and I can actually probably also go full screen. Can I go full screen? Okay, let me not waste time trying to go full screen. I can try to go full screen. That will give us a little bit of space. Alt V, no, it's
The view is not showing. F11 and
F11, yes. Yeah, okay,
Yeah,
very
yeah,
good.
yeah.
Yeah. So perfect. So yeah, okay. So what we are going to do is we are going to use this framework called Torch. Okay. Okay. So and we are going to use this data set called Cipher 10 data set. Okay. So the Cipher 10 data set is very common, and you know, a lot of the portions of this particular tutorial demonstration is also taken from there's a very nice tutorial on the PyTorch website itself. So if you look at that, much of the code is from there, but there are some things you will not get there anyway. Okay. So the first module that I want to introduce, okay, is this Torch Vision module. Okay, this Torch Vision module basically allows you to do computer vision tasks using PyTorch. Okay, and one of the components of this, so remember, so Torch is software for doing neural networks. So you can do all kinds of neural networks using Torch. You can do feed-forward neural networks, you can do convolutional neural networks, you can do recurrent neural networks, anything. Okay, most of these things you can do using Torch. And as if you remember the introduction that I gave, so anything is a neural network, right? So any directed acyclic graph where you are doing some kind of an aggregation and then followed by some kind of a nonlinear operation is a neural network. Okay, and Torch kind of allows any of these neural networks to be defined. So in that sense, it is very, very general. Okay, only thing is that the operation that you have to do. So aggregation operation is of course multiplication and summation. So those are all inbuilt or included in torch. Okay, but the nonlinear operation has to be implemented in torch. Okay, we'll come to in a minute how. Okay, but the main thing here is that these operations have to be implemented, because what happens is torch not only implements the operations, but also it implements the derivatives of those operations. So in fact, you can also implement operations, and so torch is so another good thing about torch is that it is open source. Okay, so you can look at the source code of torch on GitHub. Okay, now it so turns out that you can also implement some of the operations, though that is going to be a little bit more difficult job. I mean, it's not so easy, but it is possible. Okay, and anyway, so most of the commonly used activation functions are all implemented in torch. Okay, okay, now okay, so now the first thing I'm going to do, but before we we go into this so another thing is that we are not going to design any convolutional neural network. Okay, so if you, in fact, let me just go to this. I was just looking at it earlier because of the some of the this thing, and this is the tutorial from where much of the code was taken. Now in this tutorial I just want to highlight one thing. Okay, that they talk about this kind of a convolutional neural network. Okay, this convolutional neural network is basically, if you remember, so what we are doing here is basically we are so they are defining this 2D convolution. Okay, where yeah, so where basically I think this is the filter size. Okay, let me just yeah, so so this is the input channel, this is the output channel, and this is the filter size. Okay, so three things you have to specify: the input channel, the output channel, and the filter size. Okay, yeah, okay, so and then there is a max pool, which is a 2x2 max pool. Okay, and then again a convolutional layer. Okay, again input channel, output channel, and filter size. Okay, and then so you see, and okay, so let me say one more thing, that this convolutional neural network will operate on this Cipher 10 dataset. Okay, now Cipher 10 dataset, the image sizes are 32 cross 32. Okay, cross 3. So 3 is, it's a 32 cross 32 RGB image. So your image size is going to be 32 cross 32 cross 3. Okay, so basically what will happen? You see, yeah. So here you have this. So the moment you have this 32 cross 32 cross 3. So 3 is anyway. So the first filter has to be 3. So you can see that the number of input filters has to be 3 here. Okay, number of output channels here is 6. Okay, and you have a filter size of 5. Okay, so so by default it I think it uses yeah it does not use padding. So in that case so this is going to be -2, right? So 32 minus 2. Okay, the output size is going to be 32 minus 2, so which is 30. Okay, Now this max pull 2D is going to divide the image by 2, so it becomes 15 cross 15. And then again here, okay, hold on a second. So here the so the filter size is 5. So yeah, so your output size here after this second convolutional layer is going to be yeah. So here, so this should match. So the number of output channels here should match with the number of input channels here. Okay, so this is matched, but the output size here. So the number of output channels is 16. Okay, and the filter size is 5 here. Okay, so let me just go back here. So basically you see this fully connected layer should have the number of input neurons, which is basically the size of the number of output channels of this one, which is 16, times actually the image size. So here they are saying that image size is 5 cross 5. So this, so which means that here basically your image output image size should be 5 cross 5. So which is kind of not matching, which means that probably they are doing an input of some other size. Anyway, so anyway, so this is the thing. So and then, so this is how you basically match the input and output of a convolutional neural network. Okay, so this is a very simple convolutional neural network that they are doing. Okay, you see the depth of this convolutional neural network is basically 5. Okay, yeah, it may work a little bit, may not work. Okay, yeah. Okay. No. So they are doing, see. So these are the layers they are defining. Okay, but they are doing conv1. So conv1 is this layer. So they are applying the input image by conv1 ReLU and then applying pool, and then conv2 also they are applying pooling. Okay, so now it makes sense. So what is happening here is, out of 30, so 30 went down to 15. Again, 15 minus 2 is kind of 13. Okay, and then 13 by 2 is basically 14 by 2 is 7. So again, somewhere there is a mismatch, because so yeah, so it should come out to be 5. The output size of this X after this pooling should come out to be 16 cross 5 cross 5 basically. Okay, that is where, and after that you do a flatten, and then you input it to FC1 and FC2 and then FC3. So FC1, FC2 and FC3 are matching because the output of FC1 is 120, input of FC2 is 120, output of this is 84, input of this is 84, and then final one should be equal to the number of classes. Okay, so this is how the network is going. Okay, but what we are going to do is we are going to look at one of the existing network, and we are going to get this existing network from this torch vision package dot models. Okay, and we are going to get the VGG11 network. So let me get the VGG11 network and show you. Okay, so if I run this, so it gives something, but at the end of it, it shows you. So there is this network architecture which is already predefined. Okay, so you can just get this network architecture. So, and you can also see, so if you just print this network architecture, so this model is now basically a VGG11 model. Okay, so if you now print this VGG11 model, it will show you the entire network architecture. So how is it? So it's a sequential model. So sequential is basically the function that allows you to define the layers one after the other, okay, in PyTorch, okay. And then yeah, so in the tutorial they have not used it, but you can use it, okay. And then the first layer is a Conv2D layer, okay, 3 input channels, 64 output channels, okay, and kernel size is 3x3. Here they are also printing, so even if you don't specify, the default stride is 1 and default padding is 1, okay. Okay. After that, there is a ReLU, and then there is a maxpool 2D, and then again there's a kernel size of 2 and a stride of 2. Okay. Again, Conv2D layer. Now the input channels will match to the output channels here. Okay. Output channel here is 128. Kernel size is 3x3. You can see that as I described, the VGG always uses small size kernels, so 3x3 kernels, okay. And in some places it will use, so in VGG 11 it is not using that. It's like Conv2D followed by ReLU followed by maxpool, again Conv2D. Yeah, so here you can see there are 2 Conv2D and ReLU, and again another Conv2D and Conv2D ReLU followed by maxpool, and then Conv2D ReLU followed by maxpool. So this is the feature extractor. So this is roughly, I mean, if you count everything, it's 20 layers, but it's actually just 11 layers, 11 learnable layers, okay. And then that is followed by an average pooling, followed by some linear layer. So linear is basically this feed forward, fully connected layer, okay. And input features, output features, ReLU. Dropout is something I did not describe. It is used for to prevent overfitting, okay. Yeah, so you just have to specify a dropout probability. Normally you can just specify 0.5 probability, okay. But yeah, so and then 3 linear layers. Basically these are fully connected layers, okay. So this is the architecture of VGG 11 model, not the original VGG 16 and VGG 19. Those are much larger models, okay. Okay, so this is our model, okay. So the model is now loaded, okay. There is one thing I have sort of commented out here, which is this dot summary. So this helps you with the computation. Only problem is that it is not compatible with the CUDA thing, okay. So if I because I will be running this model on a GPU, I have to, so I have set up this torch installation such that it works with the GPU, okay. So so that's why this will not work. But if you are using CPU, you can use this torch summary to very easily visualize the output sizes of each of these layers, okay. So that is the other thing, okay. Okay, now the next part is you have to get the data sets, and again for Cipher 10, Torch Vision module actually provides you the data set. So you can just there is a data sets module in the Torch Vision, okay. You can just take the Cipher 10 data set and you can store it in ./data wherever you are running this, okay. And yeah, so train is equal to true will get you the training fraction, and download is equal to true, obviously. And then yeah, so and then you can also transform it. So for example, here we are doing 2 transformation. One is we are obviously reading it and making it a tensor, and also we are normalizing the data to these are the so there are 3 channels RGB. So each channel we are normalizing to mean 0.5 and standard deviation 0.5. So this is a simple Gaussian normalization, okay. Okay, and now our train loader, I mean our train set has the training data, our test set has the test data, Okay, and there is this again. This is torch. TU is torch.utils, which I have also downloaded, or which I have also imported rather. Okay, and here this provides this data loader class, which allows you to iterate through the data, and it does things like batching and randomization. So so you can use this batch size and shuffle, and it can also use multiple workers and so on and so forth. So yeah, so you can use this train loader to actually feed these data to the neural network. Okay, and classes are basically the names of the classes. Don't bother with that so much. Now, so let me just run this particular cell. Okay, yeah, so it has downloaded and verified both the training and the test set. Okay, now, so the first time you run, it may take some time to download. Okay, because I am running the second time, it is very fast. Okay, uh, now here this part is about visualization. So this is about getting the data set. So I've gotten both the data sets, and now this part is about the visualization. And for visualizing, we are just doing this I am show. So we are unnormalizing, and then we are getting the image in the numpy array, and then we are just using this matplotlib. So we are using this matplotlib tool, which I described in the last hands-on session, and we are just simply showing the using this plt.imshow. We are just showing that image. Okay, uh, yeah, so this is the this is our imshow method, and now we are simply calling it. So you see this train loader, when we use the iter construct of Python on this train loader, we get the get a iterator from this particular train loader, and then we can, every time we call next on this iterator, we get a new set of images and labels. Okay, and let me just show you this. So it will give yeah, it is taking some time. Yeah, so it is giving me the next batch of images. So I have taken batch size to be I think 8 here, somewhere here. Yeah, so I've taken batch size to be 8. So it is getting 8 images at the same time. So if I let me choose this to be 16 and see. Okay, so if I choose this to be 16, it should be getting 16 images at a time. Okay, yeah, it's getting the 16 images at a time, and it is also getting all the all the class labels for this. So the first one is horse, second one is truck, third one is plane, again a horse, again dog, horse. So all these classes. Okay, so so there are 10 classes, and you can see images of all these 10 classes. Okay, I mean not here, maybe all of the 10 classes are not present, and you can run it again. Okay, you can run the next, and it will give you a different set of images. Okay, so now it is giving you a different set of images from the same train loader. Okay, so this is also sort of demonstrating how this iterator works. Okay, so you keep doing next, it will keep giving you the next set of images. Okay, so this is how this works. Okay, okay, so now okay, so if this part is clear, then now next thing is you have your train loader set up. Okay, you have to now do the computation. So one thing I want to mention here is that each of these, any computation that you do on image is inherently expensive. Okay, because images are data wise, they are very big objects. Okay, so it is, so right now what I'm doing is I have this untrained model. Okay, I have stored it in this model. Okay, earlier itself I have downloaded it. This is not a pre-trained model, so this is some kind of a random model. Okay, so this has some random weights. Okay, and these models I have got here. I have got the train loader. Okay, and now I want to see how good or bad is it doing, for example. Okay, so what will I do? Okay, and here the first thing that I'm doing is I am using this CUDA device. Okay, so first of all, I'm checking here whether the device is actually available. So I use this torch.device. So torch.device will check whether a GPU is available. If the GPU is available, it will set it to CUDA. Otherwise, it will just set it to CPU. Okay. So in this case, as it turns out that the CUDA device is available. Okay. And so I move this model to the GPU device using this model.toDevice statement here. Okay. And then what I do is I'm just initializing so I want to compute the accuracy. So I'm initializing the number of things I've got correctly. Okay. And I am also printing the size of the training data set. Okay. So this should be something like 50,000. Okay. For Cipher 10. Okay. Now, and then I am iterating over the train loader. Okay. So again, you know, the for loop can also be used to iterate over the train loader, and I'm getting X and Y. Okay. And then X is the image. Okay. Which also I am moving to the CUDA device. Okay. And now that both model and X are on the CUDA device, I am computing the output. So this output is also now in the GPU. Okay. So this output is actually giving me the probability of all the classes. So it's a vector of size 10 for each input. And remember, here train loader is giving me a mini batch of size. So yeah, I have taken batch size as 16 here. So it will give me a mini batch of size 16. Okay. And then so for each of these 16 examples, this torch.max will give me the index of the class which has maximum probability. Okay. So that is what this is doing. Okay. And I'm storing it in y hat. Okay. And then this y hat, I now have to compare with y, which is in the CPU. Okay. Device. So I bring this y hat back to CPU. This is just 16 numbers, class index, right? So this is not too much data. So I can just compare using the CPU very, very efficiently. Okay. And then this is, you know, some computation I am doing to basically compute the number of cases where we are matching. Okay. So I'm just so I'm just doing something like equal to, and then I'm using this int function on each of these guys to actually convert the true false, the boolean basically thing, to integer 0 or 1. And then I'm getting the list of ones here. And this is actually, this map function is a Python function which so it sort of sets up a map operation. So it's a this thing, and then when you actually say list, it actually creates a list out of this particular map, and then you can sort of count the number of ones this nil list. So I have used NumPy. You can use anything. Okay. So if I do this, yeah. So you see it is taking some time now. So it is doing the computation. It has computed the device time very, very quickly. Okay. Okay. By the way, one more thing I just wanted to show you, for those of you who have never run using a GPU, you can use this NVIDIA SMI. So let me just Control C once. Okay. See, you can use this NVIDIA SMI command to actually visualize the computation that is going on in the GPU. Okay, so you can see that right now the GPU utilization is 0%. Okay, and it is using about so I have a 6 GB GPU. Okay, it is using about 1.6 GB of that. Okay. Okay, and now its computation is done. Okay, so what it is saying is out of 50,000, it has got only 15 of them correct. Okay, so this is the thing. Okay, now let us see. So you can also load a pre-trained VGG. Okay, using this, and I have also downloaded this. So again, if you try to load a pre-trained VGG, it will again try to download all the weights, and the weights are in millions. So again, it will take some time to download that, but I have already done it. And now, so here we are doing the same computation as we did earlier, except that now the model is pre-trained VGG and not the random VGG that we saw. Okay, so that is the only difference. Okay, and this is this thing, and now again it is doing the computation using pre-trained VGG, and I don't know. Yeah, see here now it has increased to 83%. So 83% GPU utilization. Okay, and let us see how many it gets correct with the pre-trained. Okay, and you see it has only gone to 42, and the reason is that this pre-trained VGG is trained using your ImageNet dataset. So ImageNet dataset, first of all, you saw that the image sizes are very different. Okay. Secondly, so the other thing is that the ImageNet dataset may be normalized in a very, very different manner and fed to the VGG model. Okay, so you see it is doing very slightly better than if you were to use random, but nowhere near. I mean, it's not even very close to optimum performance. Okay, so now we want to do something. We want to, let us see. So we want to now do the optimization, and here this is going to be, so now I'm trying to train the model here. Okay, so when I try to train the model, a few things, let me first explain here. Okay, so if I have to train the model, so the first thing I have to do is I have to now define the loss. So I have defined this criterion as the cross entropy loss. Again, like I said, most of the activations and losses are already implemented in Torch. Okay, so I am just taking it from torch.neural network module. Okay, and I am using the cross entropy loss here, and I'm also using from the torch.optim module. Optim is the optimizer module. I am taking the SGD optimizer, and I am setting a certain learning rate. Let's say learning rate of 0.001 and a momentum factor of 0.9. Basically, I will keep 0.9 times the last gradient. Okay. Okay. So you can change it. I mean, you can just play around with it. Mainly, you should play around with the learning rate, but also you can play around with momentum. But if your method is not converging, you should maybe reduce the learning rate and try. Okay. Okay. So this is one part, and I am again once more setting up the data loader. So data loader, remember, is the iterator that feeds data to the optimizer. Okay, and this time I'm taking a high batch size because I know that it will work and it will be much more efficient. Okay. Okay, this part I am doing I'm randomizing the parameter. So let me first not randomize the parameter. So let me just comment this one out and see what happens. Okay. Now this one I'm iterating for a certain number of epochs. So let me just iterate for 2 epochs here. Okay. And yeah, so I'm taking the data from the train loader. This enumerate is basically just adding an index. Okay, I. Okay. And then I'm taking inputs and labels. Now here, one thing is that since I have to compute the loss and also propagate it back to the weights, and the weights are there in the GPU. Okay. So I have to also pass the label to the GPU now, because my loss computation will require the true label. Okay. Okay. And then optimizer.zeroGrad simply makes the gradient from the previous iteration 0. So there is a certain thing here. So just know that before every update you have to do this optimizer.zeroGrad. Okay. Okay. And then now I'm just passing the input to the model. Okay. Getting the output. Then I'm computing the loss using outputs and labels. So output is the predicted label, and this label is basically the true label that I have got from the data. Okay. And then I'm calling this loss.backward. This loss.backward actually calculates the gradients of loss. So whichever output node I give. So in this case, I have given loss. So it will calculate the gradient of loss with respect to every parameter in the model. So the model already knows what are the parameters. So it will do that. Okay. And then optimizer.step will simply do the step where it basically updates the parameters using this gradient. Okay. So let us start running this. Okay. Yeah. So it is now running this cell. You can see that this cell is running. Yeah. And yeah. So in the beginning, it had a loss of 0.55. And now the loss is going down. It is taking 500 images and updating at one time. So it exhausts in about 100 updates because it has 50,000 images. Okay. I am printing once every 20, so it will print about 5 values. I think 1 less or something. Okay. So you can see that the loss is going down now. Okay. And I must tell you that now it is 0% because probably it's finished training. Okay. Anyway, I will show you, but this is actually very, very heavy computation. Okay. Okay. So now it has done. So now I want to compute again the accuracy of the model. Okay. So let me just compute the accuracy of the model. Now it is computing the accuracy of the model, the training accuracy of the model. Okay. So this time it has gotten 32,722 out of 50,000 correct. Okay. Okay. So you can see there is a huge improvement, just a little bit. How much did I train? I trained only for 2 epochs. Okay. And I trained starting with the pre-trained model. Remember, I did not randomize here. Okay. So let me show first for this model that I trained. Let me also show the test accuracy. Okay. Okay. So out of 10,000, it is now getting some 64,000. So I would think, yeah, exactly same. So there is no overfitting going on here. Okay. So another thing, normally when you train with stochastic gradient, sorry. So normally when you train with stochastic gradient descent, you don't get so yeah, so you it typically does not overfit. Okay. Okay. So very good. So now let me do this. Okay. So this is the entire thing. Now you can just play around with this. So the first thing I want to do, again, I want to stop, don't want to randomize the, so it will again train for 2 more epochs starting from the last parameter. Okay, this is what it is going to do. So let me do training for 2 more epochs. Let's see how that goes. So it is doing the training. Yeah. So it's, remember the loss started where it left off last time. So 0.009. Okay. And now you see the loss is not decreasing much. And you can see that it is now using 98% of the GPU, and it has almost gone up to 4.5 GB of the memory. Okay. Earlier it was about 1.2 GB or 1.6 GB. Yeah, it has come down a little bit. And you see it is again going up, coming down, so it will keep on fluctuating. Okay. So here I have not implemented the running minimum, but you should actually implement the running minimum. Okay. Okay, and then let me see. So it's finished training for 2 more epochs. Let us see what it does. Okay, it has improved a little bit more, so from 32,000 to some 37,000, and let's see how the test accuracy has improved. Yeah, so here also it has improved a little bit more. Okay, so very good. Let us try once more and then we will go back. We will I will just demonstrate with the oh, it's already time, but that's okay. Yeah, so these kind of experiments, I mean, it will I mean, unless you have super fast GPUs, it will take time. Okay, with images. So yeah, it is again going down a little bit, the loss. Okay, and then what you can do is you can again compute the okay, gone up a little bit. Okay, and yeah, so this is about 80% accuracy, right? So you can go up to very close to 90% with this. So this one has not gone up so much, but you can basically see, like, this is a sort of a particular case, but yeah, so you can go up to about 90% accuracy with this model. But yeah, so if I now let me just forget what I have learned and let me try to start running from the from random. Okay, so let's see what happens. Okay, apparently it has not randomized. because it's starting from a very small loss. Okay, let me just interrupt. Yeah, so this guy sometimes behaves weirdly, this IPython kernel, but no, it is not randomizing the. So let me just. Yeah, so let me just interrupt this and yeah, so let me just make this 2 and run, because 20 will take a lot of time to run. If I restart the kernel, then everything will be gone, of course. We can do that. And I can sort of yeah. Yeah, so I just wanted to show one thing. So let me restart the kernel. So you will see that in a small amount of time you are able to achieve. So after a few, yeah, so you will see already you are achieving more than 80% accuracy. Yeah, test accuracy is also close to 80%. Yeah, let me restart and run for, I mean, yeah, so I have nothing much more to demonstrate except that I have now pre-trained, I have put to false, and you will see that, okay, let me, yeah, actually let me run it with pre-trained false for 2 epochs and show, okay. Restart and run now. And yeah, so just to show you, this is actually, it is doing a lot of computation, okay. So yeah, yeah, so you can check also using this one, both the CPU and GPU. So here the GPU computation does not show up, but the CPU you can see it's doing a lot of things, and the GPU here you can see it's doing a lot of things. Right now it's again at 1.6 MB, but very soon it will go up like anything. Yeah, you can go for ImageNet type image, which is like a 200 plus 200. But then, yeah. So as you can see, this 32 cross 32 type image, okay, it will do very fast. So it's almost real time. That will take ImageNet type image will take like a 15-minute kind of thing. Okay? So you will get your results after 15 minutes. I mean, for a reasonable size data set. You don't need also. So megapixel images, you can simply resize to. So see, this 200 cross 200 images to a computer vision algorithm is actually already very detailed. I mean, unless you want very, very fine-grained features to come up. In that case, what you do, you make tiles. Okay, so you take portions of the image, make tiles, and these tiles are something like 200 cross 200. Okay, that's how you process, if you can, that is. Of course, it loses out on the other information of the surrounding tiles. Okay, so your accuracy may come down because of that, but yeah, if you, it's very difficult to process directly. So first of all, your existing, forget pre-trained models, even architectures will probably not work that well. So you have to then adjust the filter size and the stride and everything in order for it to work. Okay, and if you do that adjustment, basically you may also have to adjust the architecture. Okay. Okay. I don't know what it is doing. Let me just check once. It's done with these portions. Okay, it is done with all of it. And yeah. Yeah, so it has done only 6,000 of them correctly. Okay. So if I start from, remember when I started from pre-train and did 2 epochs, I was already at 37,000 or 32,000, something like this. Now it has done only 6,000 after. It will go up there. Okay, so it will go to, again, if you keep on training, it will go to 90%. But it will take a lot of time. So let me try and see how fast we can go. So that is the advantage of loading a pre-trained model and then doing a little bit of fine tuning. Yeah, you can see the loss will come down, but it will take time. Yeah, so what happens is, you see, it is in the filter space, it is in the, so it's a very strange thing. So so the actual filter weights are very bad. Okay, but it is in the same valley, same optimization valley as it would want to go. Okay, so that is why it is somewhat faster, very broadly speaking.
Maybe in that scenario it may not work.
In that scenario, it may not work. Yes, exactly. So in that case, pre-training may not give you the advantage that it would give on a natural image. Yes, yes, absolutely. Yeah, so this is something I just wanted to demonstrate. You see, it will take a few times. So if I do it for 10 epochs, maybe it will go up. This one is done. Let me go for 10 epochs. But 10 epochs will take time. So. Anyway, so yeah, so if there are some questions or something, otherwise we can just.
So for online participants, I have given microphone access to all of you. If you want to have, if you have any question or comments, feel free to unmute yourself.
That is you have to you have to understand how the filter operates. So that is like yeah. So you can look at computer vision courses basically. So traditional, not in today actually many computer vision courses also don't teach filter design anymore because of this very specific reason that filters can be learned, so they don't need to be designed.
So if there are no more questions, thank you so much, Dr. Shravanchu, for such a informative tutorial and hands-on session. And thank you everyone for attending it. I hope to see you all in tomorrow's morning session. We will
Okay.
share the notebook in sometime in the website.